Hello everybody, as Lauren said, I'm Martin. Today I will tell you something about a generative-based model. In order to start with that, I will first introduce some simple problems. Yeah. So imagine that you want to learn how to classify two categories. In this case, there are the blue points and the red points. So you can do it in a way where you directly train the discriminative model to just predict to the posterior over each class, which means that in this case, the classification and it is meant to optimize this problem. But we can also go the other way around. That was kind of popular approach before, where for each class you train the generative model. The problem of that is that this generative model usually is somehow constrained, like for example Gaussian, and it doesn't give the great performance compared to the performance of discriminative classifier. So if we have this generative model, we can have two advantages. We can try to generate more data based on this distribution, and we can have access to likelihood. Not all generative models have these two components, but some of them have them or in some form. So let me ask about the fact if you would like to have some confidence in prediction. If we have a discriminative model, all we have is getting the probability of, for example, this green point belonging to the blue class. While if we have a generative model, we also have the joint distribution. In both cases, if you want to know how much confident we are, which means that how sharp it is, this posterior distribution on the right, and in the left, what is the value of the likelihood compared to other values, then both of these models will tell you that they are quite confident in the prediction. If you would like to classify some outlier, you can actually get from the generative model that this is an outlier and it is not confident in this prediction. While for a discriminative class, since it is very far from the decision boundary, it will tell you like 100% confidence. I know that it belongs to this class if you want to interpret the posterior distribution as a confidence. And the last example that I have, if you are on the boundary, so the discriminative model tells you, I don't know, it is 50%, which is of course correct answer. You can get the same answer from the generative model, but at the same time, at the generative model, you have the access to the likelihood, which might tell you, yeah, it is 50%, but I have seen enough examples like that. I know that this is just the thing in the data that they are distributed like that, but it is likely to be like that. So let me introduce now one specific example of generative model, and this is an energy-based model. In this case, we have a score saying that, let's say on this point, the score is something, on another place, the score is something. There is a way how to interpret it as a likelihood. And because it uses neural network, it's quite powerful and can learn very interesting distribution that you wouldn't be able to model with some Gaussians and GMMs and other stuff. But the problem of this is that we don't have any classifier. It can be extended by actually at each point having the proper score for each class, in which case this is some extension that is called joint energy-based model. This because for each point we also have this directly prediction for each class. It is also well balanced, and it has also very good discriminative performance, nearly as much as this generative as purely discriminative model. So why do we care about that? I will present some simple experiment. You can train this model, modeling the joint distribution of input and phoneme. In this sense, you take 21 frames of 80-dimensional MEL filter banks, and you want to model the joint distribution of this particular thing, where you also have the score of this being likely for each phoneme. Why I have this red thing? Because I'm trying to predict the middle part of this 21 frames. Okay, so why is it good? We have the standard way of evaluating our model, which means that we can have the same or similar performance as just a discriminator, but at the same time we can generate the new recordings, which you might ask is maybe not so useful. For this case, probably not. Also, the last thing that we can have access to is confidence. In this case, we can have some benefits. Let's say if we have ASR, we can have something like adaptive weight of the language model, which says that maybe on the parts of the input which are likely, we will not use so large weight of the language model, while on the parts of the input which would not be very likely, we might use larger weight of the language model because we are unsure of what is there. And the same can be applied in speaker ID, that we would somehow have directed the likelihood of when pulling the speaker ID embeddings over the whole recording, we might not use everything with the same weight. That is great, but what I'm trying to present is actually starting from now. So you can actually have a more benefit of having this model. And in order to do that, let me just briefly introduce the standard supervised way how you train your model. You have a data set of input and labels. You have some loss function and model. You train it to minimize the loss function. And then in an inference time, you just use the input and you directly get the prediction. But the question is, are all the inputs equally likely? The answer is no. So we might not have the same approach to test the model. So what I'm proposing is to have approximately the same training, but in a test phase, you might have multiple inputs, multiple outputs. They might be connected in very difficult, very complex ways, which I'm gonna just explain by a few examples, because it may be difficult to have some default notion about this. So the pure benefit of this model is that we might train this model only once, but it might be able to perform well or on multiple tasks. So this approach that I just described in its simplest way can be interpreted as we take some input with some initial input, and then we iterating by maximizing some particular score and changing the input until we get some input that we want to get. And for example, on this input, we can infer something that we would like to infer. This is a lot of theoretical, but we can think of this as some kind of search problem. Now I'm gonna show you a particular example, and it is how it can work as a denoiser. So we can corrupt the input recording. Then we can try to maximize the likelihood of each of the frame. You can pretty much have this as a first input, this as a second input, and so on. And we want to maximize the probability of that, which might get us to something which is similar to the original one. It's not going to be the same, but since the performance on this recording will be like very bad in terms of at least phoneme accuracy, on the middle one we can regain a lot of the original accuracy. So right now with Najim, I'm actually trying to see whether this can be also applied to protection against adversarial attacks. And the next thing is that actually the way that you saw it the last time was that I actually used that model on the whole recording by using it on each of the frame. You can do the same things to actually generate even recordings. Surprisingly, if you make your score very clever, not just the basic one, you can generate something that really, at least visually, looks like a generated speech. And the problem of that is that it has no notion of language model. So it sounds like Klingon or something. You will hear that it makes sense, but there are no words. The next thing is that how you can use it. You can actually condition each frame on the particular frame, which means that you take the test recording, you take the 200 of the labels, and you try to maximize your score with respect to be the with respect to the output in such a way that it would be the same sequence of labels. In this way, you can actually have something like that. I wanted to ask which one do you think that it is real and which one are generated, but I don't have time for that. So the real one is the middle one, and the upper and bottom one are generated. So the bad thing about this, it has no notion of speaker ID. So if you play it, you will change the speaker, but you will hear the same phoneme sequence. So this is what you saw the last time. And in order to deal with these problems, we can have, I propose to have a different thing. You can actually also have a speaker loss at the same time, and then have one joint energy-based model for modeling speaker and input, and one modeling the phonemes and input. In which case, you might be able to improve the previous task of TTS, and this one doesn't even solve it, but you can also incorporate language model in a similar way. And if you do it, it opens possibilities to use this model in these ways. So for example, voice conversion would take the recording and just take the speaker embedding, while it would keep the same sequence of the phonemes. You could use it in the same way impeding, while you would have everything fixed. Yeah, it's last slide. So this impeding is the same thing, just changing the particular phoneme. And also it could be used even more in more advanced way, for example, for source separation, where you would iteratively try to remove something from the utterance in order to have a high likelihood. And the last possible way that I can think of it right now is if you actually fix some kind of activation in neural nets, you might try to sample another inputs with the same fixed activation, which might give you few samples, and it could help you to some interpretability. Okay, thank you for your attention. Do you have some questions?